Hello. In this lecture, we'll define a regular surface in real three-dimensional space. Okay, so let us begin. Okay. Uh, so let us take a subset S of R3. So let S be a subset of R3. Okay. So this S will be a regular surface if it satisfies the following properties. So S is said to be a regular surface. So if for each point P belonging to S, okay, so there exists an open set B in R3, okay, containing P and there exists a map sigma defined on an open set U of R2 to B intersection S So the sigma is defined on an open set U of R2. Sorry, this is R2. Such that the following holds. Okay. So such that the following holds. Okay, so maybe I can draw a picture. So this is my R3. And I have some subset, something like this. And I have taken a point. So this is my S and P. And now, so suppose there exists an open neighborhood P of this P. So this is my, say, P. Okay. And there exists a open set U in R2. So this is open. And there exists a map, so which takes this U2. So this this portion. So this is my B intersection S. So this map is sigma. Okay. So the sigma will satisfy the following properties. So if sigma satisfy this following properties, then we say this S is a regular surface. Okay, so first, so what we want, so this sigma is differentiable. Okay, so this will imply what? So if I write, so sigma ub to be equal to x ub, y ub, z ub. Okay, so sigma differentiable, it means that so all the partial derivatives of this x, u, z exist. So del x, del u, del y, del u, del z, del u, del x, del v. So all these partial derivatives exist. Okay. And the second condition is so this sigma is a bijection and it is a homeomorphism. That is, sigma and sigma inverse are continuous. Okay, so the first property is sigma is differentiable, and the second is the sigma is a homeomorphism. Okay. Okay, so if these two properties are satisfied, so we call this S to be a differentiable surface in R3. And third is this regulatory criteria. So what is this? So regulatory condition. Okay, so what is this regulatory condition? So this sigma, if I take the differential of the sigma, so d sigma q is injective for all q belonging to this open set U. Okay, so note that this d sigma q, it is a map from R2 to R3. Okay, so this is a linear map. So this is a linear map. So saying that this linear map is injective, so if you get, if you take the matrix corresponding to this differential, so the rank of that matrix, it will be equal to 2. Okay, all right. So this is the definition of a regular surface. So if these three conditions are satisfied, so then, so this S, it is called a regular surface. Okay. Okay, so now let us take, so let S be a regular surface in R3. Okay, so this means that so suppose this is the set in R3, this is S in R3. So at each point, so what we have, So we have something like this. So this is my B, and this portion is sigma of U, which is equal to your B intersection S. Okay, and I have a map from this open set U to your R3. Okay, so sigma of U is equal to B intersection S. Okay, all right. So now, so what you do? So let us take a point. So let us take a point P belongs to your U, or let us take, because I have taken P belongs to the S. So let us take Q belongs to U. Okay, so U is something like this. Okay, so this is my Q. Okay, and so the sigma UB is equal to X UB, Y UB, Z UB. So this I have taken earlier, and let us take, so this Q to be equal to U naught B naught. Okay, all right. And so if I take, so this, the curve B equal to B naught, so B coordinate is constant. Okay, so then I'll get uh, a straight line which is parallel to x-axis, and it starts from this point Q. Okay, so if I take this thing, so this is parallel to x-axis. Okay, yeah, so this is the straight line B equal to B naught. Okay, and similarly, so I have the curve U equal to U naught. Okay, so any point here, so it will be U comma B naught. So U is varying, and any point here is U naught comma B. So B is varying. Okay, all right. So now let us take this curve. So take the curve sigma U of B naught. Okay. So take the curve. U goes to, so U is varying. Okay. So U goes to sigma U B naught. Okay. Or if you want, I can write like this. So alpha U is defined to be sigma U of B naught. Okay. All right. So let me draw once again this thing. So this is my point Q, and I have this curve here, and I have this map which goes onto this this surface patch. Okay, and this is my sigma Q, and this curve, So this I have called it to be my alpha. So sigma of alpha, it will be something like this. So this is sigma of alpha u. Okay. And similarly, I can define, so define beta b to be equal to sigma u naught comma b. Okay. So then, uh, yeah, so, yeah. Okay, so one mistake I have made in the diagram. So if you map this straight line by sigma to this thing, so this will be in fact the curve alpha. So this is in fact the curve alpha, and beta is defined in this way. And if I take this vertical line, okay, so image of this, so this will be your beta. Okay. All right. So now, if I take d sigma q, okay, and now let us take, so before that, let us take, so let E1, E2 be two unit vectors uh, along the lines B equal to B naught and U equal to U naught. Okay. So U1 is this unit vector here, and E2 is this unit vector. Okay. So now if I apply d sigma on this E1, okay, so d sigma, it is a linear vector, so it will take to a vector, okay, in R3. So what will be that vector? So this is nothing but alpha prime u. Okay, so this is the tangent vector. So you'll get this alpha prime u. All right. Okay. So similarly, if I take d sigma q of E2, so this will be equal to beta prime b. Okay. So again, let us come back to this d sigma q E1, so which is equal to alpha prime u, and recall that alpha is u is sigma u v naught. So what you are doing here, so recall that alpha u is sigma u v naught, which is again equal to x u v naught y u v naught comma z u v naught. Okay. Yeah. So here, note one thing, that so I have taken d sigma E1. So this E1, it starts from this vector q. Okay. So this will be alpha prime u naught. Similarly, d sigma E2, it will be b prime v naught. Okay. So this will be alpha prime uh, u naught, and alpha u is this thing. Okay. So therefore, alpha prime u naught, so this will be del x del u evaluated at the point u naught v naught. So then del y del u evaluated at the point u naught v naught. Maybe I can write it here. So del x del u naught v naught, del y del u at the point u naught v naught, del z del u evaluated at the point u naught v naught. Okay, so this in short will write as d sigma du evaluated at the point, okay, evaluated at the point u naught v naught. So this is my notation. Okay, and similarly, if I take d sigma q e2, so this is del sigma del b evaluated at the point e naught v naught. Okay, all right. So therefore, what we have here, so this alpha prime u, this tangent vector is nothing but your, so this is alpha prime u naught. So this is del sigma del u at the point u naught v naught. And similarly, for the curve beta, so I'll get a tangent vector here. So this is del sigma del b at the point u naught v naught. Okay. Yeah. So yeah. So note this thing. So we have taken this d sigma to be injective. Okay. So this will tell you that, so these two vectors, del sigma del u and del sigma del b, okay, they are linearly independent to each other, and they will generate a plane. So that we will call to be tangent plane. So since this differential is injective, so this will imply that, so these two tangent vectors, so del sigma del u at the point q and del sigma del b at the point q, okay, are linearly independent, okay, and they will generate a plane which is called the tangent plane of S at the point Q. Okay, at the point sigma of Q. Okay, all right. So we have defined regular surface. So now it is a time to see some example. Okay, so before going to this examples, so let me also state this thing. So this alpha u and beta b, so they are also called coordinate curves. So alpha and beta are called coordinate curves. Okay. So now let us give few examples. So first, if I take any plane, so let P be a plane in R3. Okay. So how do you give a parameterization of this plane? Means how do you find a map from an open set of R2 to R3 such that the image will be plane and that map will satisfy all those properties mentioned in the definition. Okay. So now suppose you are given this plane. So this plane is given, and now let us take a point here, A, and okay. So any point in this plane, you can write this as follows. So we can take two unit vectors. So let us take, so take two unit vectors E1 and E2 such that E1 is orthogonal to E2 and E1, E2 are parallel to this plane. Yeah, so we have something here. So this is my E1, suppose, and this is my E2. And so this vector, you can displace it here. And any point here in this plane, you can write like this. So let us take B belongs to P. So then, so B is always equal to A plus X E1 plus Y E2 for some XY belonging to this R. Okay. So now what you do, so you take sigma XY to be equal to A plus X E1 plus Y E2. So the sigma, it is a map from this R2 to this P. Okay, and you can check that. So this sigma, it is a homeomorphism, it is a differential map. Okay, and T sigma, okay, it is yeah, it is injected. Okay, so check that P is a regular surface. Okay, and the second thing, second example, so let us take a sphere, unit sphere in R3. So this is the equation of unit sphere in R3. Okay, and now what we do? So we'll take a map from an open subset of R2 to your R3 such that the image will be a subset of this S2. Okay. Okay, so how we are going to do that thing? So suppose this is my R3, and now let us take the sphere. Yeah, so this is my unit sphere. And now let us take this function. So sigma theta comma phi. So this I'll take it to be equal to cos theta sin phi, sin theta sin phi, comma cos phi. Okay. So this theta pi, so these are my spherical coordinates, okay, in the sphere. Okay. So how do you get this point? So suppose this is my point P. So how to get this thing? So you take this straight line, and this is my origin, and this angle is my phi. Yeah, so if phi is equal to, so phi equal to 0, so what I'll get? So sigma theta 0 is equal to 0, 0, 1. So we'll get this point. Okay. Yeah. And if I take this line, so this is my x-axis, so this is my y-axis, and this is my z-axis. So this angle is theta. Okay. All right. Now let us take, so let u to be equal to theta comma phi, where this theta, it is varying in this open interval, and phi is varying from 0 to pi. Okay. So what will be my sigma of u? So sigma of u will be the following. Yeah. Okay. So if I take theta equal to 0, so sigma 0 phi, so this will be sin phi 0 and cos phi. So what we'll get? So you'll get this. So you'll get this great circle. Okay. And so this this part, it is, so theta is varying from 0 to 2 pi. Okay. Yeah. So this part, so this point, it will be not there, and phi is varying from 0 to pi. Okay. So this means that sigma of u, if you delete the semicircle, okay, if you delete this semicircle from the sphere, okay, so that will be your sigma of u. Okay. So sigma of u, it is S2, and sigma of u is equal to S2 minus C. Okay, so what is my C? So C is the semicircle as given in the picture. Okay, and similarly, so you can find intervals, okay, such that, or similarly, you can find B. So suppose this semicircle is my C prime, okay. So you can find, or maybe, so find B such that sigma of B is equal to S2 minus C prime, okay. And clearly this S2, so this is U union this B, okay. Sigma is differentiable. Sigma is homeomorphism onto its image. And also you can check that. So check that. So d sigma, this differential at any point Q belongs to U or B is injective. Okay. So here we got two open sets U and B, and the map is same on both the thing. Okay. Such that all the conditions of the definition of regular surface holds. Okay. So this implies that. So therefore, so this S2 is a regular surface. Okay, so I'll stop here. We'll continue in the next class.